Welcome back to GFun Facts Online. Today, we are going to dismantle the image you have in your head of the red planet. When you close your eyes and picture Mars, you likely see a desolate, rust-colored sphere, a place of freezing deserts and silent, dusty winds. But we are going to take a journey back in time, about 3.5 to 4 billion years ago, to a version of Mars that would look shockingly familiar to you. We are talking about a world of blues and greens, a planet with cloud-dappled skies, thundering river systems, and vast, calm seas that mirrored a younger, fainter sun. This was a world of oases. Some of these oases were the size of continents, others were hidden deep within impact craters, but all of them were places where the chemistry of life may have bubbled in the warmth of a tropical climate. For decades, the scientific story of water on Mars was incredibly simple, and, frankly, a bit boring. The consensus was that Mars was a frozen, desiccated world that might have seen a few brief catastrophic floods before freezing over again. It was the cold and dead paradigm. But that story is wrong. A revolution is currently underway in planetary science. Thanks to recent discoveries from NASA's Perseverance and Curiosity rovers, combined with high-resolution orbital maps, we are now uncovering evidence of a Mars that was episodically warm, wet, and shockingly tropical. We are talking about a planet that sustained active hydrological cycles, rain-driven weathering, and stable lake systems for millions of years. So let's trace these ghost waters of ancient Mars, starting with the most recent and startling evidence coming from the ground itself. We need to talk about Jezero Crater. You might know Jezero as the landing site of the Perseverance rover, but billions of years ago, this crater was a body of water the size of Lake Tahoe. In late 2024 and throughout 2025, scientists analyzing data from the rover identified a specific type of rock scattered across the crater floor that simply should be there if Mars was always a cold, icy desert. These are the float rocks of Jezero. They are called float rocks not because they hover, but because they were transported from the crater rim and deposited on the floor by water. The mineral inside them is called kaolinite. Now, kaolinite is an aluminum-rich clay mineral, and on Earth, it tells a very specific story. You don't get kaolinite from a sudden flash flood, and you certainly don't get it in freezing conditions. You get it through a process called intense chemical weathering. This happens when rock is relentlessly battered by warm, slightly acidic rainfall for hundreds of thousands, if not millions of years. It is the mineralogy of the Congo, the Amazon, and the humid tropics of Southeast Asia. Finding kaolinite on Mars is a smoking gun. It implies that the watershed feeding Jezero wasn't just wet, it was subjected to a high-energy, rain-soaked climate. It means Mars didn't just have water, it had weather. It had clouds, it had storms, and it had a water cycle robust enough to leach bedrock down to its aluminum skeleton. As Perseverance climbed the sedimentary fan, which is a massive river delta at the crater's edge, it began reading the layers of history like pages in a book. The bottom layers of this delta are rich in smectite clays. Smectite forms in pH-neutral lakes. This tells us that the early era of this lake was the Goldilocks era. It was calm, long-lasting, and potentially habitable. But as you move up the layers, the story changes violently. Sitting on top of those fine clays are massive boulders, some as large as cars. These top layers speak to a violent change in climate. We are looking at massive flash floods that tore across the landscape, carrying heavy debris. This transition paints a picture of a climate that was dynamic, shifting from a stable, tropical oasis to a chaotic, flood-prone system as the planet began its long death spiral. But while Jezero grabs the headlines, it was merely a puddle compared to the massive bodies of water that once dotted the Martian surface. New orbital mapping has revealed a network of paleolakes and inland seas that rival Earth's largest water bodies. If we travel deep into the southern highlands, we find the ghost of a giant called the Eridania Basin. Roughly 3.7 billion years ago, this was not merely a lake. It was an inland sea holding more water than all of Earth's Great Lakes combined, an estimated 480,000 cubic kilometers. What makes Eridania truly fascinating is not just its size, but its energy. Spectral analysis from the Mars Reconnaissance Orbiter has detected massive deposits of seafloor minerals like saponite, talc, and carbonates. On Earth, this specific mix of minerals forms in deep-sea hydrothermal vents. This is a massive revelation for the search for life. These ancient vents would have pumped heat and mineral-rich fluids into the cold waters of the Eridania Sea. This created a chemical gradient, which is essentially an energy source that life can exploit without sunlight. Many biologists believe life on Earth began in exactly this kind of environment. Eridania stands as the most compelling target for understanding if life ever started on the red planet. Further to the south lies the Argyre Basin, an impact crater so colossal at 1,800 kilometers wide that it likely hosted a liquid ocean the size of the Mediterranean Sea. And Argyre wasn't isolated, it was part of a global system. It was fed by river channels like the Uzboy, Ledon, and Morava valleys that stretched for thousands of kilometers, connecting the southern highlands to the northern lowlands. This suggests a planet-wide groundwater and river system, where water flowed from one oasis to another. Evidence even suggests that the Argyre Ocean remained liquid for millions of years, potentially protected by a thick ice cover as the climate cooled. This would have created a subglacial lake environment, similar to Lake Vostok in Antarctica, which we know is a prime habitat for extremophiles on Earth. But as the surface of Mars began to dry, the water didn't just disappear into space immediately. Much of it went underground. We see evidence of this in places like McLaughlin Crater. This deep crater shows evidence of carbonate-rich clays that formed inside the crater, not washed in from outside. This indicates a groundwater-fed lake. As the surface became hostile, these deep, fed-from-below lakes would have been the final refuges for Martian life, protected from radiation and extreme cold. Similarly, in Columbus Crater, researchers found alternating layers of sulfates and clays. This is what geologists call a bathtub ring. It shows a lake that slowly evaporated, fluctuating between fresh and salty phases. This cycle of drying and refilling drives chemical complexity, which is often a precursor to biological activity. Now you might be asking yourself, how is this possible? How could Mars, which is further from the Sun than Earth, be tropical? This brings us to the Noachian period, roughly 4.1 to 3.7 billion years ago, and the famous faint young sun paradox. 4 billion years ago, our Sun was about 30% dimmer than it is today. Under normal circumstances, Mars should have been an ice ball. The new scientific consensus points to something called episodic warmth. Mars likely wasn't a tropical paradise all the time. Instead, it may have been a cold, icy world, punctuated by periods of intense volcanism or orbital shifts that thickened the atmosphere with greenhouse gases like carbon dioxide, methane, and sulfur dioxide. During these windows, which could last tens of thousands to millions of years, the ice melted. These were the great thaws. Rain fell, rivers carved the valley networks we see today, and those kaolinite clays formed. Even if the average temperature was low, the equatorial regions would have experienced tropical conditions during these peaks, creating these stable oases where life could gain a foothold. But the tragedy of Mars is that this tropical era was doomed from the start. Around 3.7 to 3.5 billion years ago, the lights went out. Deep inside Mars, the molten iron core ceased its convection. The planet's global magnetic field, its force field against the cosmos, sputtered and died. Without a magnetic shield, the solar wind began to strip away the Martian atmosphere. The maiden mission measured this process directly, observing ions being ripped from the upper atmosphere in a process called sputtering. As the atmosphere thinned, the pressure dropped. Liquid water could no longer remain stable on the surface. It either boiled away into space or froze into the crust. The chemistry changed too. The planet transitioned from the Phalosian era, which was clay-rich, neutral pH, and friendly to life, to the Theakian era, which was sulfate-rich, acidic, and hostile. The oases dried up, leaving behind salty, cracked mudstones, which are the graveyards of the Martian hydrosphere. Today, our robotic explorers are sifting through the wreckage of these ancient worlds. Perseverance is currently collecting samples of that clay-rich delta front in Jezero. These chalk-sized tubes of rock are destined to be returned to Earth in the 2030s via the Mars Sample Return mission. Scientists will scan them for biosignatures, looking for patterns in carbon isotopes or microscopic fossil structures that only life could create. Meanwhile, Curiosity is climbing Mount Sharp in Gale Crater, literally driving through the timeline of the Great Collapse. It has recently moved from the clay-bearing unit, which represents the wet, habitable past, into the sulfate-bearing unit, documenting the exact moment the oases began to die. But the future of exploration lies in going deeper. If life existed in the Eridania vents, or the groundwater of McLaughlin Crater, its chemical fossils are likely buried too deep for current rovers. Future mission concepts propose drilling meters into the ice-cemented ground, or exploring the chaos terrain where ancient aquifer waters burst forth, bringing deep biosignatures to the surface. In conclusion, Mars serves as a haunting mirror to Earth. Both planets started with vast oceans, thick atmospheres, and the chemical ingredients for life. One retained its shield and blossomed, the other lost it and froze. By tracing the ancient tropical waters of the Red Planet, we are doing more than mapping geology. We are asking the most profound question of all: was the universe lonely from the start? The clays of Jezero and the seabeds of Eridania suggest that for a brief shining moment, two blue marbles circled the sun. One is still blue. The other is now red. But in the dry dust of its ancient oases, the memory of water, and perhaps the memory of life, endures, waiting for us to find it. Thanks for listening to G Fun Facts Online.